Hello everyone, this is Ashish and welcome back to Spacecast. It is the fifth episode. It is that one podcast on rocket science and technology, and we are going to talk about all the interesting topics that you guys are having wondering about space technology, space science, and the universe itself. So, in the community post, I asked you guys to ask some questions, and I am here to respond to those. And let us start without wasting any time because we want it to be fun introduction and all. We'll keep on having the new people. You'll understand what it is over time. And the first question over here is the highest rated question. It is having 9 likes. Again, not that high, but still, now our podcast is small but solid at the same time. What are the types of sensors, actuators, microprocessors, and microelectronics generally used in rockets? Now, I'm a mechanical engineer and I was in launch vehicle side. I was in liquid propulsion in my time in Indian Space Research Organization. So I can maximum answer as a mechanical engineer. Okay, obviously do not expect me to answer in the form of an electronics engineer. But yes, there's every now and then collaborations between different streams of engineering. So I'll start with actuators. So the most biggest highly used actuator would be the gimbal actuator. So for you to understand what is a gimbal actuator, first you'll have to understand what is gimbal itself. And for you to understand what is gimbal, you'll have to understand why is it required. So there's something, if we talk in a technical manner, there's something that we call thrust vector controlling. So thrust obviously is a vector. It is a form of a force. So it will be having some direction, and it is having a direction opposite to the direction of motion of the launch vehicle. Launch vehicle in common terms would be known as a rocket. All right. So rocket, if it wants to go up, the thrust has to go in the downward direction. If it wants to go to the left, it has the thrust on the rightward direction. What if it wants to go northeast or it wants to go upward and rightward? Then the thrust has to be downward and leftward, right? So for simple people, in simple language, you can understand in a manner of Newton's third law, action and reaction. But I've explained in the 3 misconceptions about rocket science video that it is not actually Newton's third law. It is conservation of linear momentum. But in a simple manner, you can understand that you are throwing the exhaust in the direction opposite to the direction that you are actually trying to move. The conservation of linear momentum is also going in the similar direction. As a matter of fact, it is nothing but something derived from the Newton's third law only, where it says that if you are throwing mass with some velocity in the leftward direction, you will have some mass thrown with some velocity in the rightward direction, exactly opposite, but the product of mass and velocity will remain the same. Similar concepts are used in rocket science. So coming back to the point, you are having some thrust, but if you want to control the direction in which you are going, basically you'll have to control the direction in which you are producing the thrust. So the thrust is coming out of a rocket nozzle. Now rocket nozzle is not really going to look like a nozzle. A nozzle, generally what you would have seen while watering your plants, would be something which is converging. The area of cross section is decreasing, right? But when you look at a rocket nozzle, it is going to be diverging. The area of cross section is increasing. That is mainly because the velocity of the exhaust is supersonic over there. And your basic things, like if you increase the area, the velocity will decrease. If you decrease the area, your velocity will increase. That actually happens in the opposite manner when it comes to supersonic flow, especially when, basically, if I'm talking about that, it is compressible flow, and the compressible flow regime is completely different. So over there, up till some point, if I say it is the Mach number, if the Mach number is equal to 1, till that point you will need a converging nozzle, and after that you will be needing a diverging nozzle to continue on increasing the velocity. So the diverging nozzle that you're seeing is actually a converging diverging nozzle, but only the diverging section will be visible from the outside. Actually, it will be a converging diverging nozzle, and always, this is something that always happens for primitive mechanical engineers. You can even see it in a venturi meter, that the converging section is going to have much shorter length, or the angle of convergence will be much higher than the angle of divergence. And the main reason for that would be flow separation. Flow separation creates vibration. Maybe we can talk about that in another particular video. But what you're seeing is the diverging section of a converging diverging nozzle. I don't really know where I got here from, but that nozzle that you see, from that the exhaust is coming out, or we can say the burnt propellants. What is a propellant? Propellant is a name given to both fuel and oxidizer, whatever a rocket carries with it. Basically, if we talk about the fire triangle, for a combustion to take place, you will need fuel, you will need oxidizer, and you will need heat. All right, for if these three things are present, then definitely combustion will take place. Okay, for sustained combustion, you will have to give certain amount of heat. Those are different things. But if you have these three, then you will have a combustion. So rocket has two things carried out along with it. That is number one, oxidizer, and number two, fuel. The oxidizer and the fuel both can be called as propellant in general. So the burnt oxidizer and fuel, or the burnt propellant, is thrown out of this nozzle, and the direction in which it is thrown out, that is the direction of thrust. All right, now thrust is also of two different kind. There's one pressure thrust. We are going to talk about that in some other point. Basically, I'm trying to explain what is actuator, and I've somehow explained the whole rocket science over here. But anyways, you understand what is thrust vector. So thrust vector, let us say for the simplest case, is going to act in the downward direction. Okay, now I want to control the direction of thrust. Now this direction of thrust can actually control the direction wherever you want to go. How can you control or signify the motion of a spacecraft or a rocket? You can say it is defined in form of pitch. Pitch will move somewhere like this. If you're looking at the video version, you can be able to understand, or you can understand if the frontmost part of a launch vehicle is named as nose, then the nose moving up and moving down will be termed as pitching, and the nose moving left and right. All right, so it is going to rotate the whole launch vehicle moving left and right. It is going to be known as yawing, and the whole launch vehicle rotating about its own axis will be known as rolling. Now all the three motions can be controlled by your gimbal control, right? So I'll say right away that rolling cannot be controlled by only one gimbal or only one rocket engine itself. You'll need a cluster rocket engine, or at least you'll need some other methods of controlling. But pitching and yawing can easily be done by changing the direction of vector. Okay, so I'm not sure if I'll be able to explain everything using this pen only, and I'm pretty sure that the audio version people will not be able to understand. But when you're trying to when you're trying to pitch, now there's a confusion generally, because rocket is perpendicular to the surface of earth, then which is pitching, which is yawing. Now that is completely on the designer to define. Generally what happens is that rocket goes up first and then it goes sideways, right? So when it goes sideways, then it is like a ship, right? So it is almost like moving parallel to the surface of earth, kind of parallel. And when that happens, then you can say that that launch vehicle's base will be called one which is closer to the earth, and the top will be called something that is away from the earth. And then moving parallel to the base would be yawing, and moving perpendicular to the base would be pitching. All right. Okay. Now again, it is a little bit complicated for me to explain over here, but it is very tricky for you to think also. So let us say that I want the launch vehicle, for you, according to you, to turn right. Okay. Now, if it is turning right, then in which direction should I move the nozzle? That is a very good question, right? So if I have to move right, then can I move my nozzle right also? Well, think about it. See, here comes the picture of center of gravity. Now, center of gravity of a launch vehicle will be somewhere around exactly, let us say exactly at the middle of the launch vehicle. Now, when the launch vehicle has to turn right, what happens if I turn the nozzle, I mean the direction of thrust, towards left? All right. If I turn it towards left, sorry, according to you, if I turn it towards right, right? So what happens is that that thrust vector will be having some couple against the center of gravity, right? And that couple, that means couple will be something that we call torque. Torque will be force multiplied by distance between that vector from the center of gravity, and that will cause from my direction it is clockwise, from your direction it will be anti-clockwise direction, right? So if I turn the nozzle in right direction, then the couple will be formed like this, and it will be turning it to the right direction. So what I'm actually trying to say is that if you have to turn right, then your nozzle also has to turn towards right. You understand? Because you'll have to take care of couple. So things really do not work like the way we navigate on the surface of Earth. So for example, let us say that we are on a car. So we have to turn left. Which direction do you think that the wheel is going to turn? Towards left, right? It is very simple for us. We are going to turn the steering wheel to the left. You'll see the wheel turning towards the left, and we are going to move towards left. But over here, yeah, kind of, it is in a similar manner, because your nozzle is going to turn left, but the nozzle is behind you. All right, so you can think about it in a little bit in a manner how the boats would work or the ship would work, right? So most likely I was able to explain it in a proper manner, but if you still have some questions, you can put it in the comment section in YouTube, or you can send me a voice message on Anchor, or if you're on Spotify. I do not think Spotify is giving you anyway. Okay, so now you understand the thrust vector controlling. Now this thrust vector controlling is done by gimbal, right? So the gimbal will be sitting at the top of there's something that you can, if you have ever heard of a universal coupling will be like two hooks, and it will be having the direction of motion left and right, and front and back, right? So an engine will be just hanging free from the stage. All right, what is a stage? Stage is basically the major part of the launch vehicle that you see from outside. Engine will actually be a very small part. So the stage will be having the navigation and guidance. It will be having the processor. It will be having all the helium gas bottles and all the pressurizing gas bottle, and every other accessories the stage will be having. Okay, now stage is the major part of the launch vehicle. The engine, which is actually producing what is useful for the launch vehicle to move, it will be just suspending freely. Okay, without the actuators, it can be moved anywhere, and the actuator will actually move the direction of the thrust, right? So these actuators are called gimbal actuators. And finally, coming to the point, this is the question actually that was asked over here, what are the kind of actuators that are used. So the two types of actuators that I have seen are, number one, mechanical actuators, and number two, which are electromechanical actuators, right? So electromechanical actuators will be very small, and mechanical actuators will be humongous. Okay, now newer launch vehicles are using more towards electrical direction, so that it is more concise, decreases the weight, and weight is the biggest enemy of a rocket. Okay, so what a mechanical actuator would be using is the exhaust gas itself. Okay, so the exhaust gas that is coming out from the turbo pump. Now I've talked about this before when it comes to liquid engine. Yeah, already I should mention it that I'm talking about the actuators of the liquid engine. There are actuators of solid engines also, and they are very different. All right, and there are various kind of thrust vector controlling. It's a whole chapter, and people who are wondering which book I should read when it comes to rocket science, I would definitely suggest read the book Sutton. And it is a very costly book. If you go and buy it, it is going to cost you somewhere around 10,000 rupees. But if you are filthy rich, then definitely go ahead. But I'm pretty sure that you're going to find some alternative methods also. But coming back to the point, I'm talking about the liquid engine thrust vector controlling, and it can be done using these kind of actuators. And the primitive form of actuator is using the exhaust gas of the turbo pump. So I've talked about this in my liquid engine video, where there are two combustions taking place. One combustion is taking place at the combustion chamber of the rocket engine, the major combustion, which is actually going to produce all the exhaust of the propellant and all that is coming out from the nozzle. There are other nozzles also present. There's one more nozzle that will be there at the exit of the turbo pump, and both those thrusts are coming out of the rocket engine. The other nozzle that is coming out from the turbo pump, because turbo pump, it enters the combustion chamber from the gas generator. A pre-combustion chamber will be getting inside the turbo pump. Turbo pump will be rotating the turbine, and turbine will be rotating the pump. Hence the combination of turbine and pump is called turbo pump, right? So after rotating the turbine, that gas has to get out. So when it gets out, it is also going to produce somewhere around like 7 or 8 Newton of thrust. right? But majorly that waste gas which is coming out of the turbopump, that is directed towards this actuator, and that is used to move the whole gimbal. Now gimbal will be moving the engine to an angle maximum of 14 or 15 degrees, not more than that, but that is more than sufficient to control all the direction. All right, so maybe someday I'm going to be talking about thrust vector control in a more detailed manner. I've studied it to a huge extent when I just got into ISRO, but I need a concise video for that in which I'm talking in a structured manner. All right, so that is a kind of actuator. Other forms, for example, sensors. There are huge number of sensors in any rocket engine, and that is the thing that I learned over my time as a rocket engineer, is that pressure is the most important parameter in building a rocket. From starting from assembling it, testing it, to finally controlling the rocket, pressure is everything. For example, let us say we are assembling a rocket engine. What is the biggest enemy of a rocket engine or any component of a rocket engine, you know? That is leak. You cannot have even a single small, very, very low mass flow rate like 1 kg per second. You cannot have leak when it comes to rocket engines. There is certain amount of leak present everywhere, but there is always some minimum limit that you should not go above of. Okay, so leak is very dangerous when it comes to rocket engines. So when you're assembling also, let us say you assemble part A and part B, instantaneously what you'll do is you're going to fill some gas into that assembly, and then you are going to monitor the pressure of that gas. If the pressure falls, that means that there is a leak over there. Okay, why do we fill that component with some gas? Because when it is actually in action, it is not going to have a gas, it is going to have some other gas. For example, right now we are going to test it with nitrogen, let us say, but finally when it is working, it is going to have hot gases or propellants or something or the other, anything under pressure, right? So in that situation there should be no leak, right? So we'll be monitoring that pressure while assembly. But after that also, when the launch vehicle has, let us say, has had its liftoff, after that also it is sending data down, that what is the pressure amount or what is the temperature at what part, everything is monitored. And that is why sometimes you are going to see that the launch is aborted, because the pressure, temperature, these parameters were not at the optimum level or what was expected. So that means that definitely there is something or the other wrong in your launch vehicle. Okay, so for measuring all those things, the pressure, temperature, there I think 40-50 sensors assembled to every engine, and these all sensor data will be going to a computer kind of thing, we can call it processor, and that is going to compile it, and that data is sent backwards, or before you actually put the launch vehicle, put the engine inside the launch vehicle, before the engine goes outside, that time also you can actually connect it with a computer and see if all the pressure data or the temperature data are coming properly or not, or actually it is reading or not. So the sensors are very important. There are different kind of sensors. There are few pressure sensors that is going to measure the pressure of a particular tube, and there are other pressure sensors that are called differential pressure sensors, and it is going to basically find out the difference of the pressure of two different tubes. There are so many tubes in a rocket engine, and there I would say somewhere 40% of the tubes are just because you need to measure pressure. All right, so the final stage of assembly of the engine, when everything is done, the major parts, for example, whatever I have explained in the liquid engine video, the major parts like turbo pump, gas generator, the throat and all that, everything, pogo characteristic valve and everything is assembled. After that, the final stage, the sensors are assembled. All right, and these sensors are finally checked whether they are giving the data properly or not, and then the engine goes to get assembled to the stage, and then again it is checked over there that everything is working or not. Again, pressure checks are there. There are different kind of checks. Maybe some other day we are going to talk about that. Microprocessor, like I said, I'm not going to be able to answer much in the side of electronics, but people should know that there's basically a computer sitting on the launch vehicle in every stage basically, that is going to, because see, once a launch vehicle takes off, no, there's no one from the launch center controlling the direction of launch vehicle. Okay, so it is going to be all automatic. So let us say if a launch vehicle is on the flight and it rolls a little bit because of the air disturbances or something like that, then what will happen is that that computer is going to find out how the navigation and the guidance system is going to help it find out that it is off path. So what it will do, it will accordingly adjust the thrust so that it comes back, so that the launch vehicle rolls and it is following the trajectory that it has to follow. Okay guys, all right. So more than that, I will not be able to answer in the electronic side. I think most of the questions are answered. Anindya Sinha, my God, I answered Anindya Sinha for 20 minutes. Okay, moving to the next one. What is max Q and why is it of such importance during launch? Okay, what is max Q? Now this Q, if you do not know, is a term from fluid mechanics. Okay, very simple term. What is Q? Can you think? Q is what we call dynamic pressure. There's something that we call static pressure. Now most of the time in the undergraduate level we study static pressure only, and that is nothing but rho gh, what we study. That is density multiplied by the acceleration due to gravity multiplied by the head or height. But dynamic pressure is something completely different. It is given by rho v square by 2, and it is only present when, number one, the fluid is moving or the particle is moving inside the fluid. Only in those situations dynamic pressure will come into the picture. Now, why is it important when it comes to launch vehicle? You might have seen it is generally called out during the space shuttle launches that we have reached the maximum, or they basically say max Q. What happens in max Q? Well, I'll tell you what first a launch vehicle is designed to do when it reaches the max Q. It is designed to decrease its thrust at max Q. Now why? Dynamic pressure is going to cause some kind of load on the launch vehicle, and this kind of load, when it becomes maximum, you are going to be smart to decrease the thrust or decrease your acceleration. Otherwise your launch vehicle might not be able to sustain. Or it is smart to design a launch vehicle that is not able to withstand the maximum dynamic pressure at its maximum acceleration, and design it for a little bit lower, and design the launch vehicle such a way that when it reaches maximum Q, it actually decreases its acceleration, and once it passes through that region, then it can again accelerate. Now I'll explain it properly to you guys. Dynamic pressure is given by rho v square by 2. Now rho is the density and v is the velocity. Now in this case there's a launch vehicle that is moving, the atmosphere is stable still, so that is the velocity that we are going to count, the velocity of the launch vehicle. Now you can understand that the density is going to thin out as you are going to go up and up in the atmosphere, you're crossing that, all right? And the velocity is going to also keep on increasing. So the density is decreasing but the velocity is increasing, but v is having a square, so the increase of velocity is going to be multiplied with itself, right? So there is a point, obviously, if you look at the graph of rho v square by 2, you're going to see that it is going to increase and then it is going to decrease. So there's going to be a peak of the product of rho and v square, and that is the max Q, where the dynamic pressure will be maximum and the vehicle will have to withstand that, and at that point it would be smart to decrease your thrust. Right, so it is as simple as that. The density after some point will decrease very low. After the maximum dynamic pressure or max Q has passed, the density drops so much that the dynamic pressure is not that high or is not that dangerous, and thus it is not required to have low thrust anymore. You can go back up, right? So that is max Q, the maximum dynamic pressure. Now you'll have to understand, generally the lowermost stage, or when the launch vehicle actually reaches the max Q position, solid stages are acting generally most of the time. If liquid stages are acting, they are designed in a manner that they decrease the thrust when they are in that regime. So when it comes to solid stages, I've talked about this before, that there are various kind of shapes of the solid stages. When you look at the propellants are basically casted, right? So there might be star shaped propellant, there might be circular shaped propellant, there are various forms of shapes of propellant in which they are casted. Basically these shapes that I'm talking about the shape of the hollow that is in between where the propellant is actually going to burn. So for example, if you are having a star shape, then you are definitely going to have more surface area, because star is having higher parameter when it is compared to circular shape. So that means that it is going to burn faster, right? So that means that it is going to produce higher thrust. So when you are at max Q regime, it is planned like that or designed like that, that you are having a shape which is having a lower thrust that you are putting out. So what we generally call is an M curve. So if y-axis is having a thrust and x-axis is having, let us say, time or altitude, whatever you might call, then it is going to increase first like an M, and then it is going to decrease like an M, and then it is going to increase again. That is the M curve that we generally have to deal with maximum dynamic pressure. Okay, so I think I was able to explain. If you do not understand what is dynamic pressure properly, the movement of fluid, let us say now that the fluid is moving, the movement of fluid will be having some pressure accumulated with it. If you do not understand, I'll explain it to you in the simplest form. So mechanical engineers who have been studying fluid mechanics for like one semester only, they'll be able to understand something that we call pitot tube. Now what happens in a pitot tube? Pitot tube is something that we use in airplanes to measure the velocity of the airplane. But what is interesting over there is that the flowing fluid is brought to still point at a point, and because of that there will be a rise of pressure. All right, so from the Bernoulli's equation you can understand that the summation of P by rho g plus V square by 2g plus z would be constant, right? So what happens is that if you look at the final position, the velocity becomes 0. So since the energy is conserved, then all the kinetic energy is going to turn into pressure energy. And that pressure energy is shown in the form of increase of the altitude where the pitot tube is placed, right? So that increase of altitude is because of the conversion of the dynamic energy into static energy. So that is the kind of energy that a moving fluid is having, or a moving object in a still fluid is having. All right, so I think I was able to explain max Q, but it is not a topic that is explained very well, because I was going through the internet also, but I was not able to find a lot of explanations, and especially this dynamic pressure. Not now, but I think few months ago I was trying to find good information about dynamic pressure. It is not very easily found in the internet. But still, if you have any more questions, put it down in the comment section. What are the next few questions? Okay, there's nuclear powered rocket. I want to take a little bit of break, taking simple topics for a while, then I'm going to get into nuclear powered rockets, because I'll have to explain over there again. Semi-cryogenic engine, ISRO's upcoming HLV rocket, and specifications, other heavy lift vehicles. See, I'll tell it right away. Semi-cryo engines of ISRO is going to take a long time to come up to being. All right, actually when it is manifested, heavy lift vehicle, if I'm not wrong, is going to replace the twin engine of Vikas engine, what we call L110 stage. It is going to be replaced by semi-cryo stage, and that is going to produce a huge amount of thrust, right? So, but I do not think that it is going to happen in any near future. So that is why I'm not commenting on it much. So let's move forward. These are just ideas. There are various ideas given by the organization, but I do not know when it is going to come to be. So when solid news starts to come, then I'm going to talk about that. Okay, now this one is funny. At which frequency launch vehicle and orbiter used to communicate? Which type of microcontroller or processor used in the system? Battery is used in communication satellite like GSAT-30 because they work 24/7. Sir, do you have an emergency button? So first three question I have no idea. Okay, so these are all from an electronic side person, and if I'm not wrong, the DP of Neeraj Singh Kaira is Yuri Boyka, most likely, or some UFC fighter. I do not know, but I do not know the answer to that. But these are good questions. Makes me feel that you guys are really serious about space technology. Now the next question is, sir, do we also have an emergency button? Like if something goes wrong, we press the button and the rocket explodes. If yes, then what happens in rocket when we press the emergency button? All right. So every stage of any launch vehicle is having a bunch of explosives attached to it. Now this explosive do not explode, but it will start an explosion. Why? Because the biggest explosives are already sitting in the launch vehicle. What are they? The propellants. The propellant, the oxidizer, and the fuel is already over there. So all you need is a little bit of spark and everything will blast away. So every stage will be having that system of having this emergency exit. Why? Two reasons for that. If a launch vehicle fails right after a launch, if it goes out of control, then it might go and land on human civilization and destroying a lot of lives, or it can destroy anything. Okay, there's one reason why most of the launch sites are at a very exterior location. But the second reason is that if it falls on some other countries, let us say desert or something, we don't want the other country to open up our engine and find out everything by reverse engineering, because reverse engineering is a real thing. China has proved it. Okay, so not only China, actually, okay, let us not comment on that, but there are a few guns also which has been made using reverse engineering. But yeah, so we do not want either of those, it landing on some, or let us say if we see that it is going to again come down as a missile, then we are going to explode it, and let us say fragments are going to come down. If it is too high, then it is going to be easier to burn away by the atmosphere, and if it is too low, the impact will be lower. But above all, it is going to save a country from giving its engines technology to some other country as a gift so that they reverse engineer it. Okay, so yes, Neeraj, there is some emergency button, and this emergency button is controlled from ground only. All right, so the ground people can actually press that button and it will go explode. Also, I do not know 100%, but there might be some mechanism also that means already programmed in the computer that it goes and blasts away. Okay, do all satellite need a boost to remain in the same orbit? Yes, definitely. All the satellites, even ISS, will be needing some kind of propulsion continuously. That is the life of a satellite. All right, so satellite, if to stay in the orbit, they will need a little bit of propulsion every now and then. The amount is very, very low, but yes, they will be having some fuel also over there. Okay, all right, moving forward, let us get into nuclear propulsion. So nuclear powered rocket, this is a question by a name that I cannot pronounce, otherwise I would have. But see, during 1960s, humans really became very serious with space exploration. Like they were planning to go on moon, and they were definitely not going to stop over there. They were at that time also planning to go on Mars, they were planning to go on Venus, they were trying to do their best to explore the universe. Now over time everything faded away because they believed that the fund was going in the wrong direction. But at that time only, they funded something that was nuclear powered rocket engines. All right, and basically the idea came because they understood that if you had to explore distant places, now places which are definitely going to take lakhs of years for you to reach over there, nuclear powered engines could do it better and much faster. Why? Because in a layman's term, if you look at it, the fuel of a nuclear fuel is going to have very low mass. It is not actually going to have, it is going to have very low mass when it is coming to the amount of energy that it is going to produce. The size of the nuclear fuel rods or nuclear fuel in any form that you are going to talk about is going to be very, very low. For example, if you are comparing uranium or plutonium with, let us say, compressed liquid hydrogen or UDMH and all that, it is going to definitely consume lesser space, and it is going to be lighter because it is much richer fuel. Problems are also going to come with it, but we are going to talk about that later. But the main thing that if we talk in the terms of a rocket engineer is that the specific impulse of a nuclear powered rocket engine was double, sometimes more than double, of the best chemical rocket engine that was present. So what we refer it as ISP, that is the specific impulse. And if you want to we have discussed it in the Spacecast episode 4, it was discussed with Chandan, but let me discuss it again to clarify things. It is basically the amount of time for which a rocket engine can produce 1 kg of thrust by consuming 1 kg of propellant. You understand? So basically it is saying that how long it is going to last, or how far you can go, or how fast you can go. It completely depends on how you use it, right? So the ISP of a nuclear powered rocket engine was close to 900, when the ISP of the best rocket engines of chemical form is only somewhere around like 300 or 400. You understand? So that is why it is very, very valuable, and that is why the investment was done at that time. And the early investments of the rocket engines was so, I think it was so stupid, but I do not know. You just think about it. It was in the form of explosion. They used to call it a pressure plate, and below the pressure plate you'll have literally explosions. There are videos available that they did tests also on that, and they basically did that. There will be one blast, and then the second blast, and the third blast, and it will propel in the forward direction. You understand? But then they came to a more simplified version where they are going to use hydrogen, and they're basically going to use nuclear energy to heat it. And when you heat it, the density changes. So if I talk about the basic working or the structure of a nuclear power plant, then what is there? Basically, there are nuclear fuel rods, there are control rods, so that if the reaction goes out of the control, then your control rods are going to fall in, and it is going to absorb the excess neutrons. So what actually happens is that there will be nuclear fission. Now, obviously, I should mention it over here. There are two different kind of nuclear reaction. Number one, nuclear fission, and the second one is nuclear fusion. So in nuclear fission, what will happen is that heavier atoms are going to split into lighter atoms, and in nuclear fusion, lighter atoms are going to merge into heavier atom, what we call as hydrogen bomb as well, okay, or something that is going on sun. All right, nuclear fusion, they fuse together. But here we are using nuclear fission technology, a technology that was devised before the end of World War II. Okay, the Manhattan Project and all, I'm talking about that. But soon after the World War was over, they still kept on applying these technologies to missile, or they kept on applying these technologies to rocket. And somewhere around late 1960s, they were working on this one. And what they basically did is that in like a nuclear reactor, the fission reaction will go, and basically this fission reaction is going to do nothing other than producing heat. So what is happening in a nuclear reactor is that E is equal to mc square given by Einstein is used to its best. All right, so what happens is when an atom splits, right, a uranium splits into two different smaller atoms. If you look at the mass of those two smaller atoms to a very small decimal place, it will be different. Like if you add the sum of the masses of the two atoms which are split, it is going to come lesser to the mass of the original atom from which it is split, right? So that difference of mass is converted in the form of energy, and not only any energy, mass multiplied by the square of the speed of light, right? So that energy is going to come in the form of heat, and that energy is used to run the turbines in nuclear reactors, because once you can produce heat, then everything else is just like any other thermal power plant, right? So this generation of heat can be used to change the density of hydrogen that you can carry in the form of liquid. And then when that happens, the volume that changes is in the form of, like, it can multiply it 1,000 times the original volume. And when you throw it out of a nozzle, then obviously you are going to produce a thrust, right? You are going to increase its speed, and the rest of the philosophy remains the same. And that was the idea of nuclear powered rocket engines. But the main problem was there, and the question at that time was that what if a launch vehicle fails in the launch pad? What happens? Nuclear fuels are radioactive, and the place will be radioactive forever. Okay, literally not forever, but for a long time. For your generation, it is going to be useless, right? Or a rocket engine goes and it goes out of direction and it falls somewhere else, then also that is a problem. Also, these nuclear rocket engines are having very high specific impulse, but it cannot be used as the booster stage or the first stage. It cannot be used to lift off because the thrust is not going to be that high. So anyways, these engines are going to be used in the upper atmosphere only, if everything goes well, it is going to fire in the upper atmosphere. But what if everything does not go well? Because we have seen rocket engines fail or launch vehicles fall apart all the time, right? So that was the problem, and then it was decommissioned. But recently they have again started to work on that. And I think that if you have to go further in space exploration, you'll have to rely on nuclear powered rocket engines over time, definitely. All right, next, what is the main advantage of multi-staging a launch vehicle? The main advantage would be that you are not using energy to propel useless junk along with you, right? So what happens is that there's a continuous drop in the mass of launch vehicle. Why? Because the propellant is draining out, right? So the propellant is continuously decreasing. That means that the mass of the launch vehicle is also continuously decreasing. So yes, obviously you would want that the moment a particular, let us say 1 liter of propellant is gone, the capacity that is holding, or the container that is holding that 1 liter is also gone, that mass is reduced, because now you do not need that anymore. But you can do that in certain intervals. Okay, so number one would be that once all the fuel is drained out, why are you actually carrying that? Okay, so let us say we are having only a single stage, okay, and this is the fuel. So what happens if you are reaching somewhere around half the capacity of the tank? Then basically you're carrying the rest half of the tank for waste. Okay, you are not actually using that. So it would be better if you convert it into 2 stages, and then what you can do is that you throw one stage which is empty now, and then you are left with a lighter launch vehicle at a higher altitude. Okay, now with altitude, the second point, that at different altitudes different size of the nozzle is required. Okay, now if you study it properly, there's something that we call over expanded nozzles, under expanded nozzles, and the one which is perfectly done, which is adequate. Okay, so actually what should happen, if this is a nozzle now, every amount of the fuel or the exhaust, the burnt propellant, should come out straight parallelly downwards. But generally what happens is that it expands over form, or it under expands. That is because of the atmospheric pressure. So the engine is producing some amount of thrust. Okay, now this thrust divided by the area of the outlet of the nozzle would be giving you pressure. Now if this pressure is greater than the atmospheric pressure, then what happens is that atmospheric pressure is actually fought against by the pressure created by the engine, and you'll see some kind of like a flower kind of thing. Okay, it is going to expand beyond the size of the nozzle. But if the atmospheric pressure is higher than your pressure of the exhaust of the nozzle, then what happens is that it is going to sink in. Okay, so what we do is, generally in chemical propulsion or the conventional nozzles that we use, is that the nozzles that you will see at the lower stages, that is going to be very smaller in size. Okay, because the pressure at the lower positions, or let us say at the launch pad, is going to be much higher, the atmospheric pressure, and the pressure will keep on decreasing as you go up, because the main reason of the pressure is the column of air that is above that region, right? So at the higher altitudes, you will need a nozzle which is larger in size. Why? Because let us say 2 engines are identical. That means that the thrust produced are same. But what happens at the higher altitude, if you divide that same thrust with a higher area, then the pressure will be lower, and that pressure matches very well with the atmospheric pressure, and thus you are having more economic flight. Okay, so if you are throwing away the exhaust in the sideways direction, that is actually going to waste. Left side and the right side, both direction what you are throwing the exhaust, that is actually going to fight against each other, and that thrust is not going to go in the opposite direction of the movement of the launch vehicle. So in that form also multi-staging helps, because we can have different sizes of nozzle at different stages. But there's a kind of nozzle which is called aerospike. All right, so I'm not going to talk much about that. There was one question by someone over here also, and someone in the comment section only said that go and watch the video made by Everyday Astronaut, and that is perfect. Okay, that video, go and watch, you'll understand everything about aerospike. But aerospike is a kind of nozzle that is going to be always at the optimum level, because it is actually going to use the atmosphere to find out what is the divergence angle. Okay, so you will understand more if you watch that video. Okay, but in general form, the nozzles that we are, aerospike is also having a lot of limitations, because of which it is not actually used in any rocket engine. The nozzles used in the conventional rocket engines are the ones that we are seeing right now, the converging diverging form. And in that case, multi-staging definitely helps. Okay, I'm going to take one or two more questions. Everything about ISRO boosters, rocket engines, their names, or let me make a separate video for this one. Okay, and yeah, this question is very interesting. One second. Yeah, Composite. My god, this person, I don't even know that person's name, because it is written, I think, in Telugu. But this person has asked this question, I think, 1,000 times in my comment section in every YouTube channel that I'm having. Please, can you make a video on both composite overwrap pressure vessel and mixture ratio valve? Please, sir, make both of them. Okay. This mixture ratio valve, I really do not know what you're talking about. If you can talk about in more detail what you're really talking about. Mixture ratio, there's no specific valve that is actually going to control the mixture ratio. Mixture ratio is a different topic in itself, but I can talk about composite overwrap pressure vessel, what it is. So it is basically going to use composite to form pressure vessels. Okay, so it will be having two layers. One, it will be having metallic layer. All right, it will be very thin metal, very simple thin metal. That metal is basically going to give you just the structure. All right, and over that you will be having composite linings. Now this composite linings may be made of carbon, it can be made of silicon. Different kind of composites are there, and if you look at the composites, they'll look like a tape. Okay, so what they'll do, they'll wind that tape, and then they'll properly bake it and all, so that it forms basically like a structure. Okay, it will be like one single structure, but the way that they are formed, it is wound properly. Now I do not know properly 100% about this, but this question has been asked so many times, so I have to come up with some answer or the other. When I was at ISRO, I saw some of the rocket elements made using this method, and basically the pressurizing bottles, helium gas bottle, these are the things that is going to be used to pressurize the tank. All right, so the tank which is having the fuel also going to be pressurized from the top. Why? Because that rho gh, okay, is going to decrease. As I've said, as you move up, the fuel is going to be spent, so the height of the fuel column is also going to keep on decreasing. So above the propellant fuel or the oxidizer, you are having a column of pressurized gas, inert gases, that is going to maintain the total pressure at the bottom as constant, right? So these helium gas bottles are at very high pressure. They are like close to 300 bars, right? They are the maximum pressure that you are going to see in a launch vehicle is going to be present in these bottles only. Okay, now these are made using composites, sometimes, mostly, or in the upper stages. Generally these are made at the upper stages. In the lower stages you can carry that, but in the upper stages the reward of saving even small 1 kg of mass is going to be high. So in the upper stages you are even going to see the whole casing of the solid stages, if some solid stage is used at the upper stage, is going to be made using composites. Or if you can look at the satellite, the structure of the satellite is made sometimes 100% with composites, just to save weight. So these pressure vessels made by composite overwrap system is going to be saving a lot of weight, and that is why it is used as an application when it comes to rocketry. Okay, more than that I really cannot say. I'll have to do more research. Actually, I did a lot of research. I tried to talk to some of my friends at ISRO also. If you're working in this sector, then let us talk, but I'm not able to find so far, but maybe I'll make a video on this. But please stop posting this comment in my comment section. Okay, you've already got my attention. Okay guys, I'm going to end this over here. I hope you are liking the Spacecast. I hope that you're learning a lot out of it, and keep on posting your questions. I love your questions. I'm having at least a dozen more questions that I have not answered, but I wanted to answer, but I'm going to cover in some other Spacecast. Maybe that's the way we can have Spacecast on a weekly basis. Okay, I hope that you guys learned a lot, and we'll see each other again most likely on next Wednesday. Other than that, more videos on rocket science are going to keep on coming on this channel, Ashish Ranjan, and also a lot of personality development videos, art of speaking videos are going to keep on coming. I already have a lot of videos planned Also, there's a webinar going on called Art of Speaking. It is a month-long webinar. If you want to find more information about that, all the information will be down in the description box. That's about it, and I'm going to see all of you in the next one. Till then, bye.